Okay, and we're beginning.
Any questions before we begin? Anything from last time that was confusing or cool? So we're still sort of stuck in review mode, but it's important. You'll see later on when we actually start doing calculus, you'll see why I'm taking the time going through all this. Because you're going to have to be, as I said, very good with your algebra to do well in this class. It's going to seem a lot harder otherwise. I believe we're talking about domains. So we're still in 1.1. We're on domains. And I believe there were two examples that we didn't cover yet, right? So, what were they? What were they?
4 over the square root of x plus 3.
X plus 3?
Yeah.
And I don't remember what number that was, but that's an example. R of x equals. And the other one was?
2x plus 1 over the square root of 9 minus x squared.
All right, tell me what you guys think I should do. Example 1.
Multiply the bottom by square root of x plus 3.
Why?
Get the square root of the bottom.
Okay, so someone did bring this up to me the other day. It seems like when you're in algebra class and or pre-calc class, people always tell you, oh, having radicals in the denominator is a sin. Or, oh, make sure you write your answers so that they don't have negative powers. In calculus, I don't care. No one cares. That's just, unfortunately, it's just something that people tell you. It does not matter. If you leave your answer as this, there's nothing wrong with that. If you leave your answer as this, there's nothing wrong with that. There's no, as long as what you're writing down is correct, I don't care if there's a radical in the denominator or not. It's not a big deal. So we don't necessarily care about getting it to look nice. I want the domain. What do we do? Yeah. Junji, go.
So you want to find what makes the radical negative or 0, then we make those choices and the rest are right for the domain.
Okay. So he pointed out that there's a radical, and we know the rules about radicals, right? What's under a radical needs to be greater than or equal to 0, right? So that's one restriction. So here we have two restrictions. One, there's that radical, which means that your x plus 3 must be greater than or equal to 0. And the second was the fact that it's a fraction, which means that the denominator cannot be 0. In other words, x plus 3 cannot be 0. So this means at the end of the day, what we want is for x plus 3 to be strictly greater than 0. And you just solved that inequality, right? And what do you get here? X must be greater than negative 3. Now, usually, again, we want interval notation, so we have to figure out how to write this in interval notation. So, as I suggest, until you're used to it, just draw a picture. Write the guy that's the point of interest. And then you kind of shade on the line where you want to be. You want to be bigger than this number, which means that we're over here. And so you can write that as an interval. How would that look?
Parentheses. Negative 3. Comma infinity.
That's good. And again, to remind you, whether you write a parentheses or a square bracket, it makes a difference here. So that is something I would be a stickler about. It's not just how you write something, it actually means something else, right? So the parentheses means I cannot choose minus 3. It is not included in the answer. Questions on that? Let's do the second one.
to have it so that where you do 9 minus x squared is greater than 0.
Right, so we need 9 minus x squared to be greater than or equal to 0 because of the radical. And 2, we need 9 minus x squared to not be 0 because it's a fraction. And so this means we need 9 minus x squared to be strictly greater than 0. Now, how do you solve that?
Yeah. So it's like plus or minus 3, but that's always going to give you a negative regardless. So because there's a negative in front of the x squared. So even if there is a negative number is going to be squared, it's still going to end up negative.
Is that true? How will it be negative? What do you think?
The answer would be negative 3 and 3 because anything over negative 3 will get you a negative number. Anything under or over 3 also give you a negative number, so you can only have negative 3 to 3.
How do you work that out though? Let's say not everyone saw that like you saw.
You can either factor out the equation or add the x squared and take the square root. Either way.
So you can do either. One way is kind of trickier though, but I do prefer the first way that you mentioned, is the factor, right? So we learned that if we're don't have a linear equation, what you want to do is bring everything to one side and factor and then say each term equal to 0. You can do the same thing here. Okay, so to solve, and this is a general, this one was kind of easy, so we didn't have to do this, but this is a little bit more complicated. So I'm going to give you the general way that you want to solve inequalities. To solve this guy, first thing you do is you pretend it's an equal sign. And you're going to solve that equation, just how you would have solved it otherwise. Okay, so the best way, I think, is to actually factor. This means x minus 3 times x plus 3 is equal to 0, which means your x is 3 or your x is minus 3. Okay, so you have those two numbers to worry about. Now, is it a concern that they will always be negative? Well, we'll see. Again, what we're going to do is we're going to draw a picture. We're going to put in the negative 3, put in the positive 3. But now we remember that it's not an equation, it's actually an inequality. We care about that expression being greater than 0. Okay? So how do you figure out where it's greater than 0? There are a couple ways. One way is to just test values, test some nice values, right? So let's say you can plug in a minus 4. Here you can plug in a 0. Here you can plug in 4. Right? Just pick any nice numbers that's inside any of these intervals. And you're going to take that number and you're going to plug it into the expression 9 minus x squared and see, does it give me a positive number or a negative number? Now another reason why I prefer the method of solving that you factor is that plugging it into the factored form is actually going to be a lot nicer, right? Because you don't actually care about the specific number, you just care about the sign, whether it's positive or negative. And it's going to be easier to see from the factored form whether something is positive or negative. So for example, if I take minus 4 and I plug it into here, do I get a negative or a positive? I get a negative, right? If I plug in minus 4 here, do I get a negative or a positive? I get a negative, right? It's easy to see that. And so what I have is a negative times a negative. That gives me a positive. I want positive, so that works. Okay. Now you go here. Let me just finish this and now I'll take your question. You plug in 0. Plug in 0 here, you get a negative. Plug in 0 here, you get a positive. Negative times positive is negative, which means I don't want that. The middle won't work. Oh, I think I know what you're going to point out. That is backwards. So this should actually be negative. I just saw it when I was doing it, because I think I do it the same way you did. I saw the picture in my head. The picture in my head wasn't agreeing with what I was saying. I'll talk about the picture in my head afterwards. But this is the way you calculate it. Okay. So I was doing it and I'm like, that doesn't make sense. I'll tell you about that later. Right? Which is good, because you can catch yourself in mistakes. This is good. Okay. So that was actually backwards. So it turns out that if I plugged in a minus 4, this would give me a positive. times a negative. And so that's actually negative, so I don't want that. Here, if I plug in 0, that would give me a positive times a positive. So the middle works. And here, if I plug in a 4, I would get a negative times a positive, which is negative, so that doesn't work. And so the answer is just minus 350. I think in one of my other classes I had this the other way around. I was kind of flying on autopilot. So that's one way you can get it. That's the general way, the algebraic way. It's kind of the sort of brain dead way to do it. But again, there's another way you could, your intuition could tell you, right? Because 9 minus x squared, we actually know what that looks like, right? Well, after 2 quizzes, you better know what that looks like. What does y equals 9 minus x squared look like? This finger is a shape to me. So. Upside down parabola, right? Where it goes up to 9. It will cut here at minus 3, it will cut here at 3. So from the picture, you can see where the graph is going to be positive and where it's negative. Notice that on the outsides, it's negative. On the inside, it's positive. Right? So even without doing all this, I could know in my head, oh, this is going to be positive between minus 3 and 3 because that's where the picture is positive. Right? And so when you have a picture in your head and you're doing calculations, they kind of check one another. So you'll know if you're making a mistake and you can put all these ideas together. Right? And it's one of the reasons why, another reason why being very good at algebra is going to make your calculus easier, because you have so many ideas coming from so many directions. You'll automatically, a lot of things will just be following your nose. You'll know that you're doing the right thing when you're doing it, as opposed to just flying blindly and not really being sure what you're doing. So in general, that's how you deal with inequalities. Pretend they're equal sign, find the important numbers, put them on an interval, and actually test the interval by plugging in numbers. If the expression is something simple, by simple I mean it's something that you already have a picture in your head about, you can either do it that way or make sure that you're always constantly checking yourself. Does the picture agree with what I'm calculating? Any questions? You get it, right? Something else that's important for us to know about is piecewise functions. Can someone describe to me what a piecewise function is?
It's like a function that, so they give you a condition like x has to be greater than 0, only a certain function with 0, and then like if x is greater than 0, then another function sort of works out.
Yeah, exactly. This is a function whose definition changes depending on the region of the domain being considered. Alright, so we spoke about what functions are. They are mathematical models of a certain kind of relationship when you're trying to create a relationship between two groups in such a way that each person in one group is connected to one person in the other group. And only one person in the other group. But sometimes this doesn't encapsulate the relationship we care about. Sometimes context matters. The rule isn't always the same. Sometimes it depends on what time of day it is or where it is, and etc. So to do that kind of modeling, we invented piecewise functions. So this basically changes the rule depending on the context. So for example, I could give you a function and say it's 1 if my x is between 0 and 1. But it's x plus 1 if my x is greater than 1. So here I'm giving you a function and I'm telling you the definition, but the definition changes depending on where you are. So if your x is between 0 and 1, that's the definition of the function. If your x is greater than 1, that's the definition of the function. Okay? So it's a function where the definition can change. And you will be told which definition applies. Okay? This is called a piecewise function. This is typical notation. This is always what it's going to look like, a squiggly bracket. And you'll have a list of definitions and where they work. Okay? Let's make sure remember how to read this. So let's evaluate some numbers here. Tell me what is f of 0.5. What's f of 0.4? What's f of 0.5 for this function? 1. How do you know it's 1?
Because it's between 0 and 1. The value of x.
So this guy here is our x value, that's our input. The input is 0.5. So we have to look where that would fall in our definition. 0.5 is between 0 and 1. So it means that the first line applies, ignore the second line, and the definition tells us that the output should be 1. That's why the output is 1. What about f of 0 before?
Still 1.
Still 1, because 0 before is 0.75. It's still between 0 and 1, so the first line is the one that applies, and I ignore the second. What is f of 20? 20 is greater than 1, so it falls into this region. Therefore, I take this definition. The definition says take the input, add 1 to it. So this is going to be 20 plus 1 equals 20. What is f of minus 2?
Undefined.
Undefined. There is none of these regions will tell me about what happens when x is minus 2. It's not defined. It does not make sense in our function. It is not the domain. What about graphing piecewise functions? Can you describe to me how you graph it? What do you think about it? Yeah?
Isn't it sort of like a closed dot line, kind of like an open dot, and then we move on to the next part of the domain? And then another closed dot.
Well, it might not be closed, but
Yeah.
I see what you're saying. But you draw one piece at a time, okay? So in order to draw a piecewise function, you'll have, of course, first know how to draw each individual piece of the function. Because you're going to draw all these pieces in a certain region and then you stitch them all together. They might not connect, but that's the idea. So for example, to be able to draw this function, I need to first be able to draw y equals 1. I also need to be able to draw y equals x plus 1. And then I'll kind of put these together. So if I look like y equals 1 versus y equals x plus 1, what does y equal 1 look like? Yeah?
So horizontal line at 1.
Horizontal line at 1, passing through 1. So that's what that guy looks like. Okay? But I don't always care about being at 1, right? I am only 1 when I'm between 0 and 1 inclusive. So on this picture, I'm going to put in my x equals 0, my x equals 1. And I'm on this part of the function, and I'm on that part of the function. So I'm kind of using the endpoints to guide me here, right? When x is 0, my y should be 1, so that plots this point. When my x is 1, my y should also be 1, so I plot this point, which means outside of that, I do not care about it, right? I'm going to ignore that. This is the part of the picture I'm going to draw. Similarly here, that's a straight line, positive slope, passing through 1 on the y. But again, I don't care about that entire curve. I only care about that curve when I'm strictly greater than 1. So I'm going to use the endpoints of this interval to help me out. I'm going to come over here, put that 1, go up to the function. Here, I have to open a circle. Because I want to be bigger than 1, I only care about the right side of this function, so that's what I care about. And I ignore this part. And So now when I want to graph this function, I just graph both of these pictures, but I leave out the parts that I want to ignore. So the graph of this would look like this. That's what it's going to look like from 0 and 1. And where do I draw this guy? Here? Huh? 1 above, right? Notice that when my x is 1, plugging 1 here will give me 2. So this guy should start lining up at 2. So that is the picture of my piecewise function. The pieces can connect, but they don't have to. You just follow what the definition is telling you, and you treat it. So knowing about piecewise functions, that's going to come in handy when we start talking about things like the absolute value of x, which is defined in terms of a piecewise function, as well as when we're dealing with limits. You'll see these guys popping up, so you need to know, understand how to do them. I was debating whether I wanted to talk about symmetry. You're not going to see it much in this class, if at all. Maybe it would have been better for like 1206, but I think I assigned some homework problems on it, so I should probably just quickly deal with symmetry. Symmetry is the property of being self-similar in some way. Usually you want to mirror a function across a line or a curve, and you can say that it has symmetry. Or like one part of the curve looks exactly like another part of the curve. Not all symmetries are ones that we care about, but in calculus there are two kinds of symmetries that are very useful when you get to integral calculus, which we're not going to do a lot of integral calculus in this class. There's something called talking about odd functions. These are functions with symmetry about the origin. Graphically, here's what such a function would look like. Something like y equals x cubed, which we should know by heart how to draw by now, exhibits this kind of symmetry. It has symmetry about the origin. Notice that if you take the right side, flip into the y, and flip into the x, you'll get the left side. You can also think about it as putting your thumb across the origin and rotating the picture 180 degrees. That's where the name symmetry about the origin comes from. So y equals x squared is an example, x cubed is an example of a function that exhibits symmetry about the origin. And these guys are called odd functions. Why? Because with the polynomials that exhibit this, there will be odd powers. Not all polynomials where the highest power is odd do exhibit this kind of symmetry though. They, algebraically, they must satisfy this property. F of minus x must be equal to minus f of x. So for example, notice that if my f of x is x cubed, then f of minus x is actually going to be minus x cubed, which is actually minus x cubed, which is minus x cubed, which is just the negative of the original function. So the fact that when I replace all x's with negative x, I get the negative of the original, that makes an odd function. Any function that does that will exhibit this property. There are many functions that do it. Sine of x also does this, but trig is not in this class, so that's another basic example. Y equals x does this. So these are odd functions. The thing about odd functions, why you need it in calculus, is if you're integrating on a balanced interval of an odd function, the answer is always going to be 0. And this is very useful a lot of the times. Maybe we'll talk about that towards the end of the semester, but maybe not. Another kind of symmetry that we care about is even functions. These guys have symmetry about the y-axis. So graphically, that means the following. Something like y equals x squared exhibits this symmetry. Notice that if you use the y-axis as a mirror, the left side flips right on top of the right side flips right on top of the left side. This is said to be even symmetry, symmetry about the y-axis. Even functions have this. So as an example, that's y equals x squared. Y equals x to the fourth will also do this. Y equals 1 over x squared will also do this. Algebraically, f of x, if you replace all x's with negative x in your function, it actually will not make a difference. We'll get the original function. Example. So if my f of x is x squared, notice that if I take f of minus x, that's just minus x squared, which is just x squared, which gives me the original function. Even functions are nice because if you're integrating on a balanced interval, what that means is both sides will give you the same answer, so you can ignore half the work and just do half of it and it'll work out. Again, might mention this at the end of the semester, might not. There are functions that do not behave like either of these. Anyone think they can give me an example? Yeah?
Take a parabola and just like shift it to the left, and like it will have symmetry anyway.
Okay, so give me an example. So x minus 1 squared wouldn't work. Right, that's a parabola that's shifted 1 to the right. Notice that it does not have symmetry about the y-axis. It neither has symmetry about the origin, because if I take the first quadrant and rotate it to be over the third quadrant, I do not have that picture. Right? It does not exhibit this symmetry. You will also notice that if you take f of minus x, you will get minus x minus 1 squared, which is actually just x plus 1 squared, which is not the original function. It's also not the negative of the original function. So algebraically, it's neither of these. And graphically, you will notice that it does not have that picture. So usually, these are the kinds of problems I think were in your homework. They'll ask you to determine if this function is even or odd or neither, or what kind of symmetry this function has. And this is kind of the manipulation we do. Replace all x's with negative x and see what the result is. If you get the original function back, it's an even function. If you get a negative of the original function back, it's an odd function. If you get neither of these cases, you say it's neither. That's basically what you do. It'll seem like a futile exercise, but later on in calculus, this actually can greatly simplify the amount of work you have to do. One thing that will be important for even us is knowing about increasing versus decreasing functions. How about definitions? F of x is said to be increasing on an interval I if describe to me what it means for a function to increase. How would you describe it? Here's how a math person would describe it. If f of x2 is greater than f of x1 for all x1, x2 in I with x2 greater than x1. Basically, that's a fancy way of saying it moves up as you go from left to right. That's basically what you're saying. So on this picture, here's your x1, here's your x2. Your y value for this must always be bigger than your y value for that whenever you're in this interval that we call I. So you'll always have your function moving up as you go from left to right. This is described as being increasing. You'll notice that if you're a straight line, increasing means the slope is positive. This is a super important statement. You won't realize how important it is until we talk about derivatives, but it is actually a very important statement. Half of calculus, what's responsible for it, is us really extrapolating the cases that happen to a straight line, believe it or not. Everything we know about straight lines, we try to apply this to general functions, and we end up with calculus. So that's what increasing means. Decreasing is the opposite. f of x is said to be decreasing if f of x2 is less than f of x1. So that's saying the f of this value is always going to be less than the f of that value. So this means you're moving down as you go from left to right. If f of x is a straight line, then this means slope is negative. That actually ends section 1.1. So the homework for that is due on Friday. Remember that on the website I posted the first 5 sections of the textbook, so if you haven't gotten it yet, you can get that and you can do the homework. Any questions? This is really a definition. We're not going to use this right now, but we will use this.
Would the homework for next section be due the next class, or?
Homework is due when I complete a section. It's due the next class.
Next class.
So 1.1, I just finished it. This was the last thing I wanted to talk about in 1.1. And so the homework for this is due. So homework for 1.2 will be due whenever I finish 1.2. And 1.2 should be short. So I'll probably finish 1.2 on Friday, and the home for that will be due on Tuesday. That's it. I won't start another section. So we can do the homework, make sure you understand everything. Yes.
So quizzes on Tuesday, since let's say we get 1.2 on Friday, how does it work? Are you just doing the last, like the sections that we did in the past?
Quiz on Tuesday will be what we did on this week.
Okay.
So
including 1.1 and 1.2.
So quiz on Tuesday is only 1.1. We've done 1.1. This is the end of 1.1.
No, I'm just confused because if we do 1.2 Friday, you said it's short. So.
Oh, if we finish that on, yeah, so 1.2 would be included in that case. Yeah. The quiz is on the previous week.